Hi, everyone, and welcome to the show today. We're going to do a webinar here on data center modeling. And the title of today's presentation is Creative Cooling Strategies in Existing Data Center Designs. My name is Paul Bemis. I am the president of Applied Math Modeling. Most of you probably know that. And we design and deliver the CoolSim application. CoolSim is a CFD modeling tool for allowing you to predict the outcome of decisions that you make in the design area of data centers. Now, I have a panelist with me today, and his name is Lauren Zweig. Lauren has been in the data center business for a long time. We've done quite a bit of work together over the years. So Lauren is a friend of mine and also has an awful lot of experience in data center creation, both in terms of site selection, construction, physical plant. A lot of experience, also international experience, Canada, Mexico, and the UK. Lauren, welcome to the show.
Hi, Paul. Thanks very much. And hi, everyone. Hope everyone is doing well today.
So what Lauren and I are going to take a look at today is an example. Him and I have done a number of data centers together. And this one is an example of one that is very often one that you see. It's about 6,000 square foot. Lauren, I suspect you run into this kind of thing quite a bit. Data centers that aren't huge, but still significant nonetheless, right?
I'd like to tell people, Paul, that you could go work for the larger data center companies that have many large data centers, but private industry and government has many, many more smaller data centers.
Yeah.
So for the group, what Paul and I discussed in this simulation is let's take an average user and create this model and make some analogies onto what we would do with this example.
Yep, and this one's a fairly good one for that. This one is an odd shape. It's not huge. It's about 6,000 square feet. But notice the size of that supply plenum right there. And this, by the way, is just a summary of the data that comes out of the pre-simulation report on CoolSim. But 1.25 foot supply plenum right there. That's probably the first thing I notice about this that is problematic. Kind of thin. The other thing here is there's no return plenum in this particular design, and at the moment it's running okay, just the way it is. It's sitting here at about 517 kilowatts of rack load, 5 kilowatts of heat, and 728 cooling capacity. But if you start to look at the geometry, there's a few things interesting about it. One of which is this angled wall, Lauren, and I, you and I have run into data centers that have some pretty strange shapes, if I remember correctly. This is not unusual, really, is it?
I'd say it's more usual, particularly data centers that are early 2000 and earlier, so the 90s, maybe even older than that. But the data centers are not purpose-built as they are today, or purpose-designed. It was more of an afterthought, and a lot of them have grown up from head ends or switching sites, which didn't necessarily need particularly the infrastructure capacities that we're having. Or put in another way, a lot of the data centers prior to 2000 timeframe were designed for 20-25 watts a square foot. They're primarily telecom switches and head ends. And as the internet came up into 2002 and beyond, we're looking at 150 watts a square foot and two-end design distributions and things like that. So this is very common. And as the physical plant infrastructure age is now getting on 20 or 30 years, people are looking at trying to retrofit. And that's probably the hardest thing to do in the data center construction and operation business is how do you retrofit something that's valuable as an asset and keep it running at the same time you're trying to make it more efficient.
Now, one of the things I want to tell our guests here, in terms of questions, feel free to ask questions at any time. There is a questions panel that you will see in the GoToMeeting interface over on the right-hand side of your display. And there's already been a question that's come in, Lauren, about the size of this data center. He's asking about slab to slab. Slab to slab, this one does have a ceiling plenum in it. It's not turned on at the moment, so there is a ceiling above, and we're going to expose that later. The room itself is 10 feet, and this subfloor is 1.5 at the moment. So slab to slab would be 13.5. Now, also here, we've got an underfloor problem. This is also something I see quite a bit of, a bunch of clutter under the floor. And here we've represented the pipes that run around to these cooling units. They run around the perimeter of the room. And we've intentionally made them quite large to illustrate a few points as we go through this presentation today. Here's a shot from the user interface with CoolSim, and you see the underfloor is quite cluttered. We've got piping in the way, we've got underfloor cable trays in the way, and there is much discussion that I hear in the business today about underfloors being a certain depth. They need to be a certain depth. And so we're going to explore that a little bit with some CFD modeling to see, in this case, whether a 15-inch floor with clutter is in fact going to be sufficient to meet the demand here. So the first thing I wanted to do is show you some results. This is what CoolSim results look like, for those of you who may not have already seen it. The output for the entire model comes in the form of an HTML output report, and it includes all these hyperlinks. Now, I'm using PowerPoint here today to show you these slides, to show you this material. But I've got the entire set of results for the base run, which I showed you earlier in terms of statistics. The base run is solved here. And CoolSim provides both written and visual representations. So first of all, I wanted to show a couple things here about this data center just in terms of its description. You see here the supply plenum is 1.25 feet, 8 cracks in the room. Flow rate through the cracks, 119. Total heat removed, 525 kilowatts. And I have my system set up when I ran this in mixed units. I don't go pure English, or this would be in tons or BTUs. You see the rack, total flow through racks, 83,000. Total rack heat load, 517. We'll come back to this in a few minutes. This is quite important to understand what the racks need to make them cool, to make them happy. And this calculates it for you. Power summary, 517 kilowatts. And so that's the text-based report. Now let's take a look at, this one is probably the most important. This is rack inlets. And what we've done here in CoolSim is we've given you a range of acceptability for class 1, recommended, and allowable servers. So if it's red, it means that it's out of the spec for ASHRAE recommended. And if it's below 64.4, it's also out. So we are seeing in this particular representation here a little bit of cold. It's too cold. You see there is a little bit of tearing right here too. It's out of spec just a little bit, but that's probably not an issue. Now in these representations, what we're doing is we're assuming that this is a uniform heat load in the rack, and we're also assuming that the racks have been properly configured with blanking panels and properly put together. So in this representation, we're making those assumptions. It's not a requirement that you make those assumptions. You can, in CoolSim, get into the rack and actually define where the heat loads are and exactly how much they are and where the gaps are. But in this case, for purposes of illustration, we're just showing you the methodology, assuming that the racks are properly configured with blanking panels and that the loads are relatively uniform across the front. So you see here,
let me interrupt for just a sec. There's a question from
yep, you're right.
On what would you suggest the current and future expectation for power per square foot?
Sure.
And I think depending on the use, you know, I go by a rule of thumb of an average of about 150 watts a square foot at this point. If you want to put that in a load per rack, anywhere from 3 to 10 kilowatts for normal operation. If you're going to use some sort of blade appliance or some high-level, high-power requirement server rack or computer rack, I've seen them as high as 20, 25. It doesn't mean they run at that capacity, but running capacity probably anywhere from 5 to 15. Mm-hmm. There's also one more that came up. Well, that's a comment.
Yep.
And the comment on this is actually an evaluation of the design more than load. Yep, that's absolutely right.
Evaluation of the design more than of the load. That's right.
And we're using this in the example, the reason for the webinar, the reason for using CFD models is to do simulations, to evaluate designs. One thing Paul started to mention earlier, where he and I have used CoolSim as a tool where after you spend the money on a model, instead of just having the model sitting there, use it operationally where you can kind of lock it out and do simulations, crack failure analysis, or the what-if conditions. And what if I bring in a customer and add 5, 10, how many ever racks? And what does that do to the respiration of the data center, both for airflow and for heat exchange capacity? So it can be very useful. But yes, it's definitely evaluations.
Now here I wanted to point out a couple of things. This is a naturally convective, what we call a natural convection room. This is a very old design. It's sort of the way that they did it in the 70s. They put the cooling units on the side like this, blow the air under the floor, and then just let the air naturally come back to the crack units. Now, a couple of things you'll notice here is, notice this bending going on right here. This is very typical. This is what happens when you're close to a crack like this. This is a very high velocity air that's coming and beginning to bend. We call that a Bernoulli effect. This is high velocity. High velocity means low pressure. So as the air is coming across here from this crack unit, very high velocity, it has trouble due to its momentum making that right-hand corner to go up like this. And that's why you often see issues associated with racks. In fact, if we take a look at the entire plot of temperature, you can see that happening. Here I'm looking at the full temperature range, and you can see right in that area that I was just showing you, we've got issues with temperature because the air can't get there. It can't make that corner due to its velocity. So air velocity under the floor is important. It makes a big difference. If you take a look at the flow rate coming out of the tiles on this model, and let me just flip this model around so we can see it. So let me normalize that. So here's the flow rate coming through the tiles as a function of color, and you can see it's very asymmetrical, right, Lauren? I mean, it's kind of all over the place, varying by a factor of at least 3, depending where you are in the room.
Right, Paul. And this is kind of typical, right? This is your base model.
Yeah. Now, the other thing I wanted to point out here is that this has a lot of clutter under the rack. We've got a lot of clutter over here in this region, yet we're getting better flow from these units that are closer to the crack unit than we are from these tiles right here. These are flow. I mean, look at this tile right here is running at 387. Compared to up here, we're running in the 700 range. Now, if we go back and we look at the air coming out again, we see that same effect. So this is airflow coming from tiles. And for one thing, we've got a bunch of recirculation going on here. We've got net bypass airflow going on. But also, there's not a lot of air coming out of these tiles because, again, it has momentum. It's just going right by. Underneath, it's going right by that tile. So now, you say, well, there's blockage. Yes, there is a lot of blockage, but the blockage in this case, interestingly enough, breaks down the momentum. If we look at it straight on, you'll see that that's a lot of blockage right under that, right in front of the crack unit here. But it breaks down the velocity and creates a situation where the velocity turns effectively to pressure, because as you break down the velocity, the pressure goes up. So that's an interesting effect here. I guess my point is, underfloor blockage, Lauren, isn't always bad, and in some cases can be good, depending upon where it is, of course, right?
Yeah, that's what we've seen, Paul. It's kind of counterintuitive, but sometimes people perceive that having a water pipe, for example, in front of a crack unit or air handler is a bad thing because it obstructs flow, which it does, but just depending on the conditions and kind of the respiration of the data center, it actually can be an advantage because it changes the velocity under the floor. And again, I like to use CFD models to make those simulations and predictions.
Now, in contrast, well, one thing I wanted to point out here is the fan curves. A lot of folks will also say, well, do you have enough pressure? If you got too much clutter under the floor, then the fan isn't going to be able to blow at its, at its rated CFM. It's not going to be able to deliver the mass airflow at its rated CFM because you got so much pressure across the fan it won't work. So in this case, we are running with fan curves on, and it's working fine. I also wanted to show the curves. These are the curves of the two fan types we have in that base model. One of them is over here on the left. These are centrifugal fans. They're downflow standard centrifugal fans. And you see here that it's able to produce almost 2.5 inches of water at 17,000 CFM at an RPM of 1061 on a horsepower here of, I can't quite remember what the horsepower is. It looks like this thing is running, I can't see the plot on this hand side, but it's running at about 12, 13 horse. Could be up here. This one is the 17.3.
Yeah, I actually thought that was more like 18 on that side.
Could be. And then over here, yeah, we've got one at 15, and this one's running at 14, so yeah, this one's probably 18 over here. The horsepower is quite high on these centrifugals compared to newer EC styles, but one thing about them is they produce a lot of pressure, 3.2 inches of water. And if we go back and we look again, I'll just back up here and take a look at the pressure under that floor. You can see what we're running at for pressure, and you can see our pressure is 1.5 inches of water max. And that's right up against that pipe near that crack unit. So there's no fear here of not being able to deliver the CFM. The question really becomes more of distribution of air through the tiles based on the blockage under the floor. So one of the things we did here, and this nice thing about CFD, you can eliminate things and look at alternatives. So here is the same design. And what I wanted to do here is clean up the floor. So I took out the obstructions in the underfloor, just to see what would happen with respect to flow coming out of those tiles. And here we have the same plot as we had before. I'll again orient it so that you can see straight down on it. And you see that it actually made the flow near these end rows worse. The obstructions, in fact, helped in this case. So again, it changed the distribution quite a bit. I think I did a side-by-side here. Yeah. Here's a side-by-side of the two. Now, I didn't hold color constant as I did this. I should have. I just let it run. So you'll have to remember that the high end is off by a little bit. But if you take a look right in this section right here, we were looking at about 300. Now with the blockage, well, that's not a fair section. How about up here? We'll take a look at this one up here. This one's running at about 700 CFM there. If we look over here on the right, we're down around 200.
And Paul, you didn't vary the tiles in this comparison, correct?
No, same. These are all 25% open.
Yep.
Yeah, right here. Now, one of the things you can do, of course, as you well know, Lorna, is put in tiles. So what we did next is said, okay, what if we added some high-flow perforated tiles in certain areas? We're having some trouble here. It's low here. It's not great there. Put some in, and we did. And it changed the behavior quite a bit. I mean, it's kind of interesting that it does change. A single tile, a single 56% tile, would not only change the place that you're at, but it'll change the dynamics of the rest of the room as well. It's kind of interesting.
Yeah, and in my experience, and I can see Lance Miller made a comment about better where there are obstructions, and that's been my experience too. And then when you change tiles, trying to change airflow up into the rack, depending on what heat load each rack has or a group of racks have, and the different open area of the tiles. I mean, it's all trial and error.
It is trial and error.
The art of having the data center breathe.
That's right. One of the interesting things is here, if you look at this tile, number 3, the third tile in, fourth tile in, on the original design was operating in the range of 900, roughly 900 CFM. Now the fourth tile in is operating here near 1800. Now that's not where we put the 56%, or we put them over here. But you see what happens is by putting 56% open here, the air velocity is primarily tangential. It allows that air to come up, slow down, and actually come out of the fourth tile more strenuously. So I guess the point is, it is trial and error. You don't always know the effect of what's going to happen by putting a 56%er in. You may drop it in one location and think, okay, it is for the rack right in front of it. But as it turns out, it may affect tiles three tiles away. It's a bit of a trial and error kind of effort. Using this kind of system will help get you close. It's not going to be perfect, but it'll certainly show you the effect that you're going to have when, in fact, you do that. Certainly, we've got more uniform flow across this first row. I mean, the flow rates are in the range of 1,1300. They're not much different than the max over here was before. But what we did get is we got more uniformity, despite the fact that we only put 56% tiles in this row. So
what is your heat load per rack?
Right now, this is standard. This is back at 750 total kilowatts. So my heat load per rack here is around 4 or 5 kW. Yeah. So anyway, enough about where we are today. The webinar is really on where we're going to go, and this particular customer wants to take this data center up over 1 megawatt. And the questions become, can you do it with a 15-inch floor, with N+1? They want it to be N+1. What about the obstructions in the floor? Modeling is a great way to find out. There's a few things you can do right offhand. The total airflow currently available is only 119,000, so we're not going to be able to get up there with our current system. We're going to have to either retrofit what we have, add capacity, or something. So the design approach we chose here was to change the units out for purposes of age and so forth to newer DSE DA150s. These are 150 kW units each. They're producing 18,000 CFM of air per unit, and they are EC fans, which means there's no belts in them. They're direct drive, and they can be controlled, variable speed controlled fans. That would give us a total cooling capacity of 1.35 megawatts. They're 150 each. They actually will go higher than that based on higher return air temps, but their nominal capacity is 150. And if we go to a little over a megawatt, the total air required at 20 degrees, assumed delta across the racks, is almost 170,000. And you see our total airflow capacity is 162. So we'd be right on the edge if we were to go all the way to 1.07 megawatts. Now, at a 30-degree delta across the servers, it drops. And it's not always clear exactly what you have for servers. Some could be 20, some could be 30, or you could have a mix of both. So somewhere between 10 or 9 and 10 DSEs are going to be required here to. So the questions become, can we put the units in the same place? What about the blockage underfloor? What about fan curves? These particular units aren't quite as strong in terms of their capacity to deliver air as the centrifugal fans are. These are radial fans. They blow out. And then what's the best configuration of the crack units? Now, a couple things here I wanted to point out. We're going to be using some metrics here. The first one I have is called Rack Cooling Index. And this is just a measure of how many of the racks are out of conformance. How many spots on the rack are out of conformance with the ASHRAE specification. This is quite easy to do in CFD because we mesh, which is we create polygons on the front surfaces, in fact, throughout the entire data center. And then we do calculations on each one of those polygons to determine what the temperature is. So we do a couple of calculations in CoolSim for the user so they can understand the data center a little clearer with some metrics. This one is RCI. The other one is RTI. This is Return Temperature Index. And this is a ratio of what do the racks need compared to what the air handlers are operating at. You want both of these metrics to be 100%. That's when it's balanced. But they do work sort of inversely, in an inverse relationship to one another. So as you reduce the air handler flow rate, which is usually too high, as you reduce it and drive this thing towards 100%, you're effectively putting less air in the room, And therefore, the racks will begin to recirculate on themselves, causing the RCI number to go up as well. So you have to be a little bit careful here. They're great for optimization. This is the one that we're primarily concerned about first. We want to make sure that we have enough air coming into the room to meet the requirement of the racks. So the rule of thumb that I use here is that it takes about 156 CFM of air to satisfy a kilowatt of heat load for a 20-degree assumption of temperature rise across the rack. If you go to a 30-degree assumption of temperature rise across the rack, that number goes down to around 100, little over 100. So you can remember it as 100 or 150, depending on what kind of service you're using. So let's take a look with those definitions now made. Let's take a look at our design. This is the base design, and what we've done here is dropped in same quantity of units. We've got 9. I guess we put one more in. There's one right here, so there's 9 units now. And we're using EC fans, as you see. Same floor, same configuration. Natural convective still. We haven't done anything in terms of containment. And let's first take a look at the summary report here. And let's take a look at our energy calculation right here and see where we are. And you see the RTI is 99%. That's pretty good. RCI high is 100%. That's also good. So these both look quite good, but the RCI low is not registering yet, which means we're way too cold. So these two metrics look good. Looks like we have just about the airflow we need, maybe just a little more, right? But all the units are running. They're running full tilt. If we take a look at the crack performance report right here, we'll see that, whoops. So if we take a look at the crack performance report, we'll see that we're running at very, very low supply temperatures. These cracks are set at the moment for performance data. They're using a performance data boundary condition, which uses a thermostat, which on these units actually sits in the return set at 75 degrees, which is a normal configuration actually for a convective room return kind of design. So we're 75-degree thermostat set, which you see the return temp is 75 degrees. Supply temp here in the 50s. Pretty cold, huh, Lauren?
Yeah, I'd like to see those temps at 65 air supply.
Yeah.
And trying to get somewhere above, 85 to 95 return air.
Right. For two reasons. One, the heat exchangers work better. 2, the lift is less on the compressor. It just doesn't have to work as hard. Furthermore, if there's any economizer whatsoever, any economizer routines or capability in the cooling units, which the DSCs do have, that window opens dramatically if the supply temperature goes up.
Right.
So let's take a look at our racks here. Here's our rack inlets, and you see this is the conformance plot for the ASHRAE base standard right here. And you see that they're not over temp, right? They're green, but there's an awful lot of blue. It's really cold.
Right. Yep, it's chilly.
But the other problem you run into here is, look, if I look at full temperature on those rack inlets, some places we've got 80 degrees, right, in these corners. Other places we have 52 degrees. So we're seeing, a 28 degree rise or variation in rack inlet temps as a result of all the mixing going on in this room. And that's very typical of a convective kind of return system. The fact that there's no separation of hot and cold here creates this kind of effect. This is what we always see when this takes a look. And also, let's look at the underfloor pressure here as well. The pressure in the same place, just to make sure that we're not getting into any trouble on those fan curves. So here is floor pressure, and you can see we're getting up around 1.3 inches of water. So it's beginning to get near the threshold, but not really affecting it that much, despite the fact, again, that it's got tremendous amounts of clutter in front of it, blockage in front of it. So if we look at our airflow distribution on the tiles here, and let me spin this around. These are all 3D plots, by the way. I'll make a note here that I'm not in CoolSim. I'm not actually using CoolSim at the moment. I'm just showing you output of CoolSim. And one of the nice things about CoolSim is that you can view the output without having to be inside the application. All I did here was export the reports. That's the same exact report that you get inside of CoolSim. I just happened to export it and then put it into a PowerPoint slide as a single frame, a single slide, where I can then use a web browser to view the results. So here's what the floor looks like in terms of flow rate. In some ways, it doesn't surprise us that much. Lauren, I still have the 56%ers in there as I did before because I just simply never took them out. And so we're getting quite a bit of flow here, and that's right near one of those 56%ers. We might not need that depending on the situation.
Right. Yeah, and that's a good point. Depending on the situation,
yeah,
you're going to look at having a combination of different percent opening tiles, some to 25, some to 50, some solids. It just depends on what the racks need in that particular row and area.
But again, nice even distribution of air coming out of the floor right here. So looks pretty good. I mean, I think we're in fairly good shape here. We still have recirculation occurring, mixing occurring. If we take a look at path lines from tiles, this one always should show that the air is just going into the racks and not making any of it come back. And you see there's a little, but not too bad. Most of it is going into the racks as it should. This is supply air. And then again, of course, we have on the underfloor, we have air coming from the crack units in. Looks pretty good. The question becomes, are we in danger of getting into trouble on those fans? So here I brought up a plot of the EC fan. You can see it's not quite as strong. Here this is the one for the DSC. It's an 18,000 CFM supply. It's called the DA150, DSC DA150. It's one of the newer units from Liebert. And running at 1165 RPM, 1.83 total static pressure, operating at 8.5 horsepower. So there it's right on the horsepower curve, comes down here, and this is the line right here, about 1.8 static pressure before it starts to roll. Now, as the pressure rises, what happens is you start to walk this curve. We call it walking the fan curve. So as the pressure goes up, the volume goes down. But it's going to hold pretty good until you get to 1.8 inches of water, and we were well below that. So we don't have any problems right now, Lauren, with fans. I think the question becomes, what happens when you have a failure, right? Because
Absolutely.
always got to worry about that.
Yeah, we're always wanting redundancy in our infrastructure.
Right. So in CoolSim, you can launch up to 4 jobs at once off the same mesh. And so you build the model once, and you're able to vary the conditions on the crack units of off, on, the volume, and temperature. So what I did is I assumed, just for purposes of discussion, that we kept the supply temp and the flow rates constant, which we would need in this case because we're already going to be starving a little bit for air because we're right on the edge of having enough air to begin with, and we're about to drop out 18,000 CFM. But let's see what happens. So here, run 0, I've turned off crack 227. Now these cracks are just names and numbers. It's most important to know where they are. So you can tell which one's off because it doesn't have a red or a blue bottom, red top and blue bottom. You see here, this one is off. So that's one of the units off in this particular run. And let's take a look and see, first of all, how we did. And it shouldn't surprise us we're having a little trouble over there, right? This is a very typical plot I see of a situation that is both too hot and too cold at the same time. So we've got some regions of the racks out of spec. We've got other regions out of the rack that are too cold, and some that are right in. Again, not unusual. You've taken this unit out, so there's not as much air coming in here, and it's starving right there. So flow rate gets affected quite dramatically. We can take a look at flow rate again and flip this around. And you see flow rate's still looking fairly normal. We've got some issues over here, though, with flow rate. It's not doing too well as well. And if we take a look at our summary report and we look at the energy, you see RTI is now 112. So we don't have quite enough air to satisfy the needs of this data center. If we take a look, we've got a total of 144, when in fact the racks want 161. Now, again, I'm assuming 20 degrees here, Lauren. I mean, the thing about modeling is you have to assume something, right? So I'm taking a worst case view of it and saying everything is operating at 20 degree delta, which is in fact not always the case, right?
Absolutely not, and everything doesn't operate all at the same time.
Right. Another point here, well made, is that it doesn't all operate at the same time, and this data center is not going to be completely full right away either. It's going to have some time to come up the curve of load. So we're looking here at worst case conditions. But no matter where I go in this particular failure analysis, I showed you run 0 if we chose run 3, which is just another one of the units shut off. It's this unit over here. I think we're going to find the same case, that it moves, the failure moves, but it's still giving us trouble in one place or another. So there's a couple ways we could solve this. One of them is to, of course, put another unit in there, right? The other one is containment. We could experiment with containment, Lauren, and kind of see what effect it would have.
And Paul, before even that, have we looked? I've asked these questions rhetorically, but have we looked at raising the set point temperatures on everything and seeing if we can just tolerate a warmer data center?
I did not, because when I looked at full range, I figured I wasn't going to be able to do it. I mean, I think we could raise set points probably with them all running. But here I'm running at 55 degrees of cold air, and I'm seeing temperatures in the 90s on some of those rack inlets. And if we take a look at our room itself, if we just take a look at 6 feet, if we, this is a 6-foot slice right through our data center. And let me, you can use keystrokes on that. So these are keystrokes I'm using, shutting off perspective. And you see here temperatures, well, they're in the 80s in this region of the room. Where the cold air comes out, it of course drops, but we're seeing temperatures near 100 degrees over in this region. I don't think it would buy you that much to just raise set point. I think you're going to get in trouble on those racks.
Right, maybe not in this case, but that's definitely something that everyone should be looking at, and I'm sure everyone does. Just trying to get more bang out of the buck of your existing infrastructure before you start spending money.
That's right.
On implementing EC fans or replacing crack units or putting in containment. You do get some bang for the buck by just raising temps.
So this is a representation of the same data center with hot aisle. Now, the reason I chose hot aisle in this case is because I prefer to use hot aisle wherever possible. And the reason I prefer that is shown right here, that the room with hot aisle containment remains relatively cool. With cold aisle containment, the room is the return for the cooling units. With hot aisle containment, the room is the supply. So to your earlier point, Lauren, the opportunity to now begin to march up the temperature curve on supply air looks pretty good, because my temperatures in this room just dropped to 60, 70 degrees. Let me point out what we're looking at here. So this region in blue, all of this blue region is the cold aisle, and the rest of the room itself. The areas in yellow and here in red, those are the hot aisles. So that's where the heat is. There is a little bit of leakage here on these end rows, and that's why you're getting a little bit of temperature in this region. But everything leaks a little. It's not surprising that, in fact, we set these to leak a little, to let a little bit of air through them, because that's normal. It's unusual. You get 100% seal. So yeah, containment gives us this opportunity. Now, if we take a look at our cooling units here, we've got them set at 65 degrees now. I went up 10 degrees on supply temp on this base model because I was able to contain and get it out of that room. And if you look at the recommended inlet ranges now, they're uniform. So Hot Aisle did a pretty good job on this design. Now, I still don't know yet if it's going to stand up to failure scenario, but at least looking at it, even if I take a look at the full range of temperature, like I said, there's a little bit of leaking, I think, on the containment at the end of these aisles, some of which is natural and normal, and some of which is probably me not modeling it quite perfectly enough in terms of alignment. But generally speaking, we've got much better ranges here. We go from 65 to 81, so that spread is a heck of a lot better than it was before. And I think the 81 is a bit of an aberration. Most of that stuff is within 10 degrees, 15 degrees of spread across that.
Yeah, let me just point out for the group also that we recognize that when you put containment on, depending on how you make your ceiling, there are potential implications on fire code and having to deal with your local authority that has jurisdiction to work through those issues.
That's right. It is absolutely true that when you contain, you have to get the fire people involved. Although there have been movements made in containment where ceilings will drop and other things will come apart based on temperature so that they're solving those problems.
Fusible links and falling panels and things like that work okay and satisfy the fire code.
One of the other things I just wanted to point out here is we still, even though it is contained, there is still a distribution on the tiles. If we go back and take a look at these tiles again, even though I've got Hot Aisle contained, I still have the same issue with airflow distribution. So depending on where the load is in that room, and these are roughly modeled as 10 kW racks, I think you could actually move them up a little bit if you were willing to put another DSE into this room. I think you could probably move this up a little higher in terms of density. But this thing's behaving pretty well here. We are getting some distribution of air, so you have to be careful where your servers are. And there's an opportunity to reset here your high density perf tiles as well. So the question then becomes, what happens in a failure mode scenario? So here's, again, crack failure analysis. This is the ability to run up to 4 jobs. No magic number with 4. It just happens to be how we have it set at the moment. But again, I'm shutting them off in the same sequence as before. Here I shifted back to 55-degree supply air temp just to illustrate the point of comparison. I wanted to compare apples to apples, Lauren, with the earlier crack failure analysis that we were running.
Absolutely.
For any one of these, I think you're going to find the thing does pretty well. So here's, again, that same crack off over here on this side. If I take a look at my recommended inlets, I'm cold. If anything, I'm cold. So here I think you could begin to say, all right, now that I've got to contain, now let's start driving up supply air temp to the point where we begin to see it drop, the RCI number dropping below 100, and then we would be in good shape. But if you look at the full range, we got a little bit of problem over here. It's not out of spec yet, but we've got a variation over there. So we might want to take a look at the containment over there. It seems to be leaking a little. But other than that, it behaves pretty well. And it behaves pretty well, Lauren, no matter what crack unit you turn off. So I just went to run number 2 here. I've got this guy turned off. I take a look at my inlet temps. Again, everything's fine. So we could go, no doubt, to 65 degrees here, or at least you could begin to go up with your simulations now and turn up that number of supply air temp and see what happens. So long and short of it is these all worked well no matter which one you go to under the failure analysis. They all behave well. And what's interesting here is I'm on the edge of having enough airflow. Again, if we take a look at our RTI number for this design, we're at 112. That means that I don't have quite enough air to satisfy those racks. So they're pulling it from somewhere else, oftentimes pulling it around from the back. And this is why, again, I point out that you can't have perfect seals on your hot aisle, cold aisle. It's actually better to let them leak just a little bit because you don't run into the pressure problems that sometimes can occur when you've got a perfect seal of hot and cold, hot or cold.
Well, sometimes we've put tiles with dampers to, modulate the airflow in the hot row.
Yeah.
Just to be able to help circulate air.
That's right. Because if you go into a failure mode, the racks are still going to want whatever it is that they need. And like I said, they need about 156 CFM per kW, worst case, at a 20-degree delta. They're always going to want that. And sometimes it's more than that because they often build the fans bigger than is required. So if the air can't come from the cooling units because it's simply unable to deliver it, or it can't be delivered efficiently to the right location, then the only opportunity it has is to wrap the air around the server itself in some way and feed it back into the intake, or stall the fan inside the server, which would be pretty much the kiss of death for a server. If it's got no airflow, it's going to go hot quick. All right. So now one other thought that we had, both Lauren and I were going through this, is the other option you could consider, is moving these units up in the air. If the subfloor is so crowded that it's a problem, one method that I've seen people do is to actually jack these things up and just turn it into a non-raised floor data center. So that's what we did here. This is effectively a non-raised floor. So we use the subfloor really for cabling and piping and everything else, and we jack the units up. There's actually pedestals you can buy from Liebert that allow you to put them up in the air. These are still attached to the ceiling. It's still a hot aisle design. You would think, well, this will work pretty well. I don't have to worry about the subfloor anymore. I don't have to worry about clutter down there. I can use it and abuse it however I want, and that should work fine, right? Yeah, not so much. What we find here is that it doesn't work particularly well in certain cases. Certainly, again, I ran these at 55 degrees just to try to keep apples to apples. So this is running, with thermostats turned on again, just like it was before. So this run, Lauren, is exactly like the first run that I did. The only difference is we jacked them up off the floor to see the effect. And interestingly enough, it looks fine. If everything is running in normal mode, it's fine. But when you go to crack failure, you run into some trouble. And let me show you that trouble. So if we take a look at path lines, this is the trouble we run into. And let me just flip this model around and turn off perspective so you can see it. Here's the problem we run into. The air gets jammed against the surface, against the backside of the containment, and can't get out. And air doesn't turn corners very well. It really doesn't like to change its direction. It is momentum. It's got to come out in a velocity. Velocity is a vector. It has a direction and magnitude. So it's coming out of those units really hard, and it's struggling to get around this corner. It doesn't want to change. It wants to keep on going over here. But of course, this one is creating pressure in this direction, so it's having trouble getting down here. Fundamentally, we've got a problem here with airflow, the direction of airflow.
Well, we have the units battling each other. That's right.
So what happens here is that, and one of these runs actually straight out failed, but let me show you one of the runs that ran. So here's one of the runs here, and you can see what's happening in terms of a recommended. It's starting to break down. So remember, these were all blue just a moment ago, and I haven't changed anything. I'm still running them at 55 degree supply air temp, but look, we're falling out of spec. And the reason we're falling out of spec, and by the way, let me show you which one is off in this case first. So we've got this guy shut off right here, right on the end. So that one's off, and that's an important one because it's the one blowing the air down this aisle, and we've shut it completely off. And what we have is, in terms of air, if we take a look at path lines coming from the crack units, what we have is, because this one no longer is supplying that pressure, and let me again turn this around just like it was before. So here we are, and this one is off. So now instead of pushing the air down the aisle, it just simply doesn't do that at all. It lets that air that's all built up, this high velocity air, come around here and just bounce off this edge of the crack unit in a wall and just never gets down the aisles. I guess the point here, Lauren, is this is a great way to find out, because it wasn't intuitive to me that that would exactly be the case. You know, I thought, well, that might work, but you never really know until you run a couple of models whether or not it will work.
Well, that's the beauty about modeling. You pay for a base model, and then you can run simulations cheap and
That's
quick.
That's right.
And, you know, I think that's the way why I like the tool. It's not perfect, but it's a really good approximation.
It's not perfect, and I'd like to point out that, you know, a lot of people try to use CFD as a forensic tool, and it's not really good at that. You can get it to be exact, but it takes a tremendous amount of time to do that. What it's better for is the elimination of bad ideas.
Yes.
So I found a lot of people using it as a way to either prove that their ideas are right, or that in fact somebody's ideas are wrong. They're bad ideas. Here's another run here, same problem. This one's down, and it's causing the same problem. So this turned out to be not a good idea. And once you make a few runs, you can understand why. What CFD is good for is providing guidance to good engineering decisions. It's not a substitute for good engineering decisions. It's a support tool to help you make better decisions.
Right. Yeah, emphasis on the tool.
That's right. So that's what we wanted to talk about today. I guess a couple of points I'd like to make. Shallow underfloor and underfloor obstructions might not be as much of a problem as often predicted. I often hear people saying, well, I don't have a 24-inch floor, therefore I can't do this or can't do that. We've just shown you a megawatt data center, 6,000 square feet, with a 15-inch floor and a lot of impediment. And one of the things we were showing is that the airflow was better with the blockage than it was through the tiles, more uniform with the blockage than without it. So I'd like people to understand it's not always a case of a shallow underfloor, therefore I can't do, or I've got too much obstructions, therefore I can't continue to use underfloor air distribution. It's case specific, and understanding what your data center looks like and where the major blockage is important to analyze. The other point here is that when you think about adding extra IT equipment, always think about the airflow required. I hear a lot of users out there, Lauren, talking about, well, I've got so many tons of cooling, therefore I'm safe. You know, and
well, you have to have the cooling in the right place.
Yeah, you got to have the air.
That's the
air in the right
both
place.
The supply and the return, or both. You know,
it's not just
air
about
and the hot air.
It's not just about cooling capacity. It's about how much air is being delivered, and that's often the limiting factor. So again, rule of thumb, 156 CFM per kW is a good rule of thumb. That's a conservative number. If you're going to put crack units in and you're striving for a particular load in the room, take the load, multiply by 156, and then see if that number is close to the number that the total cracks will deliver. Now remember, if you want n+1, then you've got to have a little room there too. We were able to show you today that you can be very close and still do okay. In other words, we were right about where we needed to be with all units running and still able to provide an n+1 situation. But you're not going to know unless you test it or model it. And you know, this is to a point you've made a couple of times, Lauren. Operators need to understand the failure mode scenario. Do you want to speak to that one a little bit?
Well, I think CFD is a perfect tool. Let me tell the group how we've used it. When I was with a data center company, a multi-tenant data center company, we created CFD models on every site, but then we also, you know, that's for design. And then we also then bought from Paul a specific license to be able to use that model and integrate it more or less into the DSIM platform. And then the operators could use it to do simulations if a new customer came in to see how the rooms would behave. And then also doing failure analysis by turning off one by one, turning off each crack unit once additional load would be placed, and to see if they could understand how their reaction and escalation procedure needed to be modified to fit the load.
Yep. Containment, not a panacea. Strange things can happen and do happen in contained environments. You and I have both seen them. One of the questions that just came in, have you ever seen both hot aisle and cold aisle in the same design? The answer is yes. It's a bad idea. One of the things about containment is that if it's too tight, and you have a failure on one side or the other, things will go up quick. Things will just go up really fast because there's no way. I mean, the beauty of a convective room, a room with no containment at all, just natural convection, is that if something fails, they'll recirculate on themselves. The racks will recirculate them on themselves for a period of time and give you a little bit of room to recover. But if you're tightly contained, particularly on, I find on cold, and you lose a cooling unit, the servers have nowhere to go. There's no way for them to get air. So it's important that you understand the containment in the failure mode situation prior to implementing it. And I would never advocate both hot and cold. Is that consistent with your thinking too, Lauren?
Yeah, I've never done hot and cold in the same data center hall. I think there's probably some situations where you could do that, but I would think you'd almost kind of carve out a certain area or a specified area for that and make sure that you have the recirculation, because then there is, I mean, it's all about getting the right amount of air into, in front of the servers and then removing it on the back end.
Right. Now, there are options like rear door heat exchangers, both forced and convective, naturally convective, that remove it at the source. And there's also, in supercomputers, they pull the heat out inside the cabinets themselves and then reject it to the atmosphere. So there are those methods. But in conventional designs, like the ones we typically run into, off-the-shelf kind of designs, containing one or the other. Generally, I encourage hot aisle containment because one of the things I notice in cold aisle containment is when the room becomes the return and you have somebody enter the room who's not aware or comfortable with what it is you're doing, they'll immediately start changing thermostat temperatures, particularly if it's a colo or something like that. I know situations that are cold aisle contained and they'll actually reduce the temperatures well, the customer comes, and then when he leaves, they'll turn them back up. It's just kind of silly to me. Okay, one of the other questions here, what are the airflow velocities below the floor? It depends on the design. The airflow velocities with those blockages were quite high, and I can back up to that and show you that. Here's adding containment. I'll just open this one, and we'll take a look at the velocities. They're quite high. The velocities at the tiles aren't that bad. But if you take a look at the velocities, somewhere in that range, it gets quite high. I don't know exactly where. But let's take a look at path lines from cracks. This is in velocity, and you see you're getting upwards of 4,000 feet per minute in some regions. Now, I don't know where that is. That's somewhere in the underfloor domain. You're seeing velocities that are that high. These are colored by velocity, so generally speaking, you're seeing velocities here that are in the range of around 900 feet per minute, 400 here, about 900 here, I would estimate that to be. And I think your high velocities are coming right on top of these blocks right here where it comes up over the top. So right in this region right here is where you're probably seeing your highest velocities. There's one right there that's getting up pretty high. Yeah, so they do get high, but high velocities aren't really an issue. There's some noise. You'll get some audio effect, but it's not as big an issue until you get to a tile. If you have high velocity under a tile, it won't come out, as many of you know. Now, there's new technologies that are being developed as well that have fins under the tiles to try to redirect the air. And we've been working with one of the manufacturers in that area. And that is promising because what that does is it breaks down, again, the velocity and allows the air to turn that corner and come up into the room. So I think you may see more of that, particularly in rooms where the subfloor is, not as deep as you would like it, and you still need to add the capacity, and you'd like to do it without changing the floor because that's a very expensive option. So using profile tiles or finned tiles may be an option that's really worth looking at.
There's also the option of using an underfloor fan. There's a lot of things that you can do. There's the comment about a recirculation gap in the second long row is a killer, and what about blocking the in-row recirculation? And I think that's an excellent idea. This is a simulation that Paul and I came up with for this webinar, and in reality, you get to a room, and if it's existing like we're simulating here, you look at all the different options. It doesn't have to be containment. It could just be blanking panels or something, either above floor or under floor. It kind of goes to the mantra: you do whatever it takes, cheaper, better, faster, to make things work. Typically, so before you start really, do heavy lifting of replacing crack units and adding crack units and things like that.
Yep. So if there are questions at this point, we certainly will entertain them. There are some coming in that we've been answering, but let me just go to this last slide. And I'd like to thank Lauren for being with us today and sharing his experience. This is our contact information in case you would like to get in touch with us in the future. Also, we would be providing a certificate of professional development for anybody who wants it today. If you want to just send me a note on email, I can prepare one of those for you. And if you would like to model other situations, or if you have a data center that you'd like us to take a look at as an example in one of these webinars, we're certainly always looking for new and different situations to analyze. So let me just hand it over to Lauren for any final thoughts or comments.
Again, I'll just emphasize the point is I like using CFD as tools. I've worked with Paul because I think, one, it's Paul, and he's very flexible in how we can kind of model and then how we can simulate, as well as using the system as an operational tool as part of a DSIM plug. So I like using it because I think it's something that helps me make predictions. And Paul, I'd like to thank you for having me on. It's been a pleasure.
Sure, no problem at all. Great working with you, Lauren. So I don't see any more questions. We're up on the hour. If you have any, send them to either one of us as email. We'll get back to you as quick as we can. And I'd like to thank you all for attending today, and you all have a good rest of your day. Thanks again.